Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at sections 3.1 exponential functions and 3.2 logarithmic functions. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. Up until now we've looked at functions that have been combinations of adding, subtracting, multiplying, dividing, and powers, which includes things like squaring, cubing, reciprocating, and roots. Things like raising to an exponent of 1/2, which is a square root, raising to an exponent of 1/3, which is a cube root, and they are the inverses of the squaring and cubing functions. Today we are going to look at a pair of inverse functions called exponential and logarithmic functions, and these functions go beyond or transcend algebraic functions. The reason that they go beyond algebraic functions is because they are not simply made up of a finite number of operations of adding, subtracting, multiplying, dividing, etc. And as such, these functions are called transcendental functions. There are other functions that we will study in Chapter 4 called trigonometric and their inverses called inverse trigonometric functions that are also transcendental functions. So let's take a look at these inverse pairs of exponential and logarithmic functions. The exponential and logarithmic function, the exponential function is very often referred to as a growth or decay function, and if we look at a graph of a growth or decay function, such as y equals 2 to the exponent x, we see this classic shape. If we perform a horizontal reflection, we see exponential decay. Now, horizontal reflection in this case means that we have 2 to the exponent -1, all raised to the exponent of x. And in this case, 2 to the -1 is a fraction 1/2. So we see that we have exponential decay when the base is 1/2, and we have exponential growth when the base is 2. In general, what this is telling us is that if we have a base greater than 1, such as 1.1, we will have exponential growth. Okay, even 1.01 is going to give us exponential growth. It's just going to grow much slower than a base of 1.1 or 2 or 3, etc. However, we do get exponential growth when the base is greater than 1. If we have a base of 0, we actually don't get exponential growth. If we zoom out, we know, if we have a base of 1, that is, 1 raised to the exponent of positive x is always going to be 1. And 1 raised to an exponent of a negative number is the reciprocal of 1 raised to the positive exponent. And that value is also going to give us 1. And if we turn off the blue graph, let's see what happens when x is equal to 0 on this purple graph. And we see that in this case, 1 to the exponent of 0 is 1. So no matter what we do here, what x values we look at, the base of 1 does not give us the classic exponential growth or decay shape. And therefore, a base of 1 will not produce, is not an acceptable base that we want. So let's take a look over here. The parent exponential function is b to the x, where b has to be positive and not equal to 1. We now know that the base can't be equal to 1 because we do not get the classic exponential growth or decay shape. The growth shape looks like this, and the decay shape looks like this. So we understand why the base can't be 1, but why can't the base be 0 or negative? Let's take a quick look at some other graphs. If the base is equal to 0, we would have to turn off the x-axis in order to see the shape of the graph. And we know that 0 raised to an exponent of 1, 2, 3, 4, etc. would be 0 squared, 0 cubed is 0. But if we have negative exponents, such as -1, 0 to the -1 would be 1 over 0. And we cannot have 0 in the denominator, so we would have undefined y values, and therefore x cannot be negative. Furthermore, if x is equal to 0, something strange is happening. In this case, we're getting an infinite number of possibilities for y, which is an indeterminate case. And we will study the case of 0 to the 0 as an indeterminate case more in calculus. However, even just looking at this graph, it does not produce the classic exponential growth or decay shape, and therefore we exclude 0 from being an acceptable base. We're also saying that the base has to be positive, so it can't be a negative number. If we have a base such as -2, looking at this graph, in fact we can't even draw the graph because it says undefined in the domain shown. For example, if x is equal to 1, negative 2 to the exponent of 1 would produce an output here at negative 2. But if x is 2, negative 2 all squared produces an output of 4. So we can see that the y values are jumping from negative to positive as x changes from odd to even. However, if x is a number like 1/2, then the exponent of 1/2 represents the square root, and the square root of negative 2 is non-real. So we are getting non-real, undefined, and changing from negative to positive y values, and therefore we are not going to get the classic exponential growth or decay shape. As a result, then, in order to get exponential growth or decay, we are choosing acceptable bases that are only positive but not equal to 1. Okay, furthermore, if we have the expression 2 to the 3, we can read this as 2 to the exponent 3 as the third power of 2. When we want to talk about the powers of 2, we write numbers such as 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, etc. 1 is the same as 2 to the exponent 0, 2 is 2 to the 1, 4 is 2 to the 2, 8 is 2 cubed or 2 to the 3, 16 is 2 to the exponent 4, 32 is 2 to the exponent 5, 64 is 2 to the exponent 6. But the powers are the numbers 1, 2, 4, 8, 16, 32, and 64. These are the powers. So the power is the output of the base raised to the exponent. The little number up here, 0, 1, 2, 3, 4, 5, 6, is the exponent and should not be called the power, because the power is the result or the output. So when we read something like 2 to the 3, or 2 cubed, or 2 to the exponent 3, the base is 2, the exponent is 3, and the power is the result of 2 cubed, which is 8. The power is not 3. The exponential function y equals b to the x represents exponential growth as long as the base is greater than 1, and the exponential function represents decay whenever the base is between 0 and 1. So we can see in this case we are excluding powers that are 1, 0, or negative. So we are only looking from 0 to 1, not including 0 or 1, or greater than 1. Numerically, some interesting facts or relevant facts about exponential functions are the irrational number e. E is approximately 2.718, but it's exactly called or equal to e. This is a number that is not rational, so it is not a ratio of two integers, and it frequently arises when we are talking about exponential growth and decay problems, like radioactive decay, population growth, or compound interest in finance. So let's make a table of values using fractions and decimals for each of the following exponential functions. On the next page, we are going to take a look at y equals 2 to the x, 3 to the x, and 1/2 to the x. And so when we do this, we're going to say if x is negative, well, let's take some easy values. If x is 0, 2 to the x is 2 to the 0, which is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. And 2 to the 4 is 16. 2 to the negative 1 is 1/2, which is 0.5. 2 to the negative 2 is 1/4. I think I'll just write it as the fraction and then the decimal in the spot. 1/4, which is 0.25. 2 to the negative 3 is 1 over 2 cubed, or 1 over 8, which is 0.125. I notice in the table as x increases by 1, the y values double. Then if x decreases by 1, the y values become half. So half of 0.25 is 0.125. Because this is like 250, half of that is 125. And half of 1/8 would be 1/16, which is what 2 to the negative 4 is. And half of 0.125 is 0. Maybe I was leaving this room for the decimal, 0.0625. Okay, so those are our decimals for a table of values here. And in the case of e to the x, I'll leave this for now. 3 to the x, if we use the same x values, we have 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, and in this case, every time x increases by 1, y is going to multiply by 3. So 1 times 3 is 3, 3 times 3 is 9, 3 times 9 is 27, 3 times 27 is 81, which, as we know, is what 3 to the 4 is equal to. If we reverse the direction in our table, as x decreases by 1, in this 3 to the x case, y divides by 3. So 81 divided by 3 is 27, divided by 3 is 9, divided by 3 is 1. Sorry, 9 divided by 3 is 3, 3 divided by 1 is 1, 1 divided by 3 is 1/3, which is 0.3 repeating. 1/3 divided by 3 is 1/9, which is what 3 to the exponent -2 is, which is 0.1 repeating. And 1/9 divided by 3, to go back in the table, is 1 over 27, which is that decimal divided by 3. We will leave that for now. And we get 1 over 81. What we see then is when we change the sign of the exponent, the power values, for example, are reciprocals. And we should really write that down as a verbal rule or a verbal connection. Changing the sign of the exponent reciprocates the output, or reciprocates another name for the output, which is power. So changing the sign of the exponent reciprocates the output or the power. I'm just going to call it reciprocates the power. Which is the output of an exponential function. Exponential function, namely base to an exponent. Okay, e, as we just saw, is a number approximately 2.718. And so if we take a base that's in between 2 and 3, such as e, then the output values will be in between. I'm not going to fill in all these as decimals. We'll leave that for calculator work. But let's just put in some of the exact values. If x is 0, e to the 0 is 1. E to the 1 is called e. E to the 2 is e squared, which is going to be some number between 4 and 9. Similarly, e is between 2 and 3, approximately 2.718. Then e to the exponent 3 will be some number between 8 and 27. Probably closer to 27 because e is closer to 3 than it is to 2. Then e to the exponent 4 will be some number between 16 and 81. Similarly, we can call this e to the -1, or 1 over e, which will be between 0.5 and 0.3 repeating. E to the -2, or 1 over e squared, will be between 1/4 and 1/9. E to the -3, or 1 over e cubed, will be between 1/8 and 1/27. And e to the -4, or 1 over e to the 4, is between 1/16 and 1 over 81. We can also take a look at a base that is between 0 and 1, and therefore produces exponential decay. Let me just write above here that these are all bases greater than 1, therefore exponential growth. We know that this is going to be exponential growth simply by looking at the y values. As x increases, y increases. But in this case, we have 1/2 can be rewritten as 2 to the exponent -1, all to the x, which is 2 to the exponent -x. And so this graph, or table of values, is a horizontal reflection of the 2 to the x case, because we are changing the sign of the x. So if we take 0, 1/2 to the 0 is 1, or 2 to the -0 is still 2 to the 0, which is 1. But now we are reciprocating the output. So if x is 1, we get 2 to the -1, which is 1/2. When x is 2, we get 2 to the -2, which is 1/4. So we're getting the reciprocal of the 4 that we had in the exponential growth case for base of 2. When x is 3, 2 to the negative 3 is equal to 1/8. And when x is 4, 2 to the negative 4 is equal to 1 over 16. So we should easily be able to reciprocate these values and get 2, 4, 16, 8 rather, and 16. Because we have a horizontal reflection, which means that changing the sign of x is going to give us, if we change the sign of x here from negative 4 to positive 4, we get the output of 16 when x was negative 4. In this next case over here, we have another table of values. And in this table of values, we are asked to make a table of values for y equals log base 2 of x, which is the inverse of y equals 2 to the x. In a moment, we are going to look at the graph of y equals 2 to the x. But if, in fact, this graph is the inverse, then we know that we can switch the x and the y coordinates to fill in the table. So here, when x is negative 4, y is 1 over 16. So the x and the y swap, so when x is 1 over 16, the y is negative 4. What I'm going to do is, I'll highlight these values so we can see that we are using these highlighted values to come up with the inverses. So negative 4 comma 1/16 becomes 1/16 comma negative 4. Negative 3 comma 1/8 becomes 1/8 comma negative 3. So all of the exponents used to be the input of y equals 2 to the x. Now we have y equals log base 2 to the x, and the exponents that were the inputs become the outputs. So the outputs are negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. Meanwhile, the outputs of y equals 2 to the x were the powers, 1/16, 1/8, 1/4, 1/2, 1, 2, 4, 8, 16. The outputs of the original function become the inputs of the inverse function. So this is 1/16, 1/8, 1/4, 1/2, 1, 2, 4, 8, and 16. Moving on, if we look at the exponential functions graphically and their properties, let's look at the basic exponential growth function, y equals 2 to the x, and its horizontal reflection, and a basic exponential decay function, 1/2 to the x. Which is growth? The growth is y equals 2 to the x, because base is greater than 1, and the decay is y equals 1/2 to the x. Again, because 1/2 to the x is the same as 2 to the negative 1 all to the x, which is 2 to the negative x, we see that there's a horizontal reflection of y equals 2 to the x to get y equals 1/2 to the x. So I think what I will do is put y equals 1/2 to the x in red. And so how are the functions graphically related? So let's go ahead and sketch these graphs. We have some tables of values. When x is 0, y is 1. When x is 1, y is 2. 2 comma 4. 3 comma 8. 4 comma 16. Right about there. And by the time I'm at 5, I'm off the page because we are doubling the height from the previous height as x increases by 1. If x is equal to negative 1, y is 1/2. When x is negative 2, half of that height is 1/4, 1/8, 1/16, 1/32, and I can't even really tell the difference in height from the y-axis anymore. But what we do see is that as x goes towards negative infinity, each time in the table of values, as x decreases by 1, we take half of the previous y-coordinate. Half of 1/16 is smaller, but non-zero. Half of that is smaller still, but non-zero. So as x approaches negative infinity in the table of values, y approaches smaller and smaller fractions, but they are still positive, and we say that y approaches 0. This is the left end behavior, which is a horizontal asymptote. And then we have the right end behavior, which says that as x approaches positive infinity, y approaches positive infinity. And the left end behavior says as x approaches negative infinity, y approaches 0. So we have different left and right end behaviors, which is different from a polynomial or a rational case without absolute value or piecewise behavior. So it's this first function that does not have piecewise behavior, but has different left end and right end behavior. So if we go ahead and graph the exponential decay function, all we have to do is perform a horizontal reflection, take every point on the blue graph and reflect it through the y-axis. We reflect through the y-axis because its equation is x equal to 0, and x equal to 0 is the boundary between positive x's and negative x's. Furthermore, a horizontal reflection is changing the sign of x. We do that through the boundary line. And so we get our exponential decay shape looking like this. And the end behavior has changed. In the red case, as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity in the red case, y approaches 0. So we want to know what exponential features do all the exponential graphs have in common. We can see that they all have a y-intercept located at 0, 1. This is, of course, as long as there is no vertical transformation. So the basic y equals b to the x parent exponential function has this y-intercept. We also see that they have a horizontal asymptote at one end or the other, depending on whether we have growth or decay, but we have a one-sided horizontal asymptote at y equal to 0. How do the y-coordinates of an exponential function change as its base changes? Well, if we have bigger and bigger bases, let's take a look on a graph. Let's take a look at just at exponential growth. If y equals 2 to the x versus y equals 3 to the x. Let me zoom in a little bit. Versus y equals 1.1 to the x. We can see that the smaller the base, the lower or smaller the y values are when x is positive. And the higher the base, the bigger the y values are when x is positive. When x is 0, all of the y values are the same. And when x is negative, the highest y values belong to the smallest base. So we can make that connection. Let me just do this. We can make that connection depending on what x values that we are talking about in the graph. Okay, so I'll add this to the lecture notes. So simply by looking at a table of values, we could see how the outputs are affected by having bigger bases or smaller bases. A similar kind of connection would be true for exponential decay. So to make exponential decay, I simply need to reciprocate the base or change the sign of x. If we change the sign of x, all of these functions become exponential decay, and we can make a similar statement about if x is negative, the bigger the, well, we'd have to be really clear because this base would actually be a base of 1/2. This base would be a base of 1/3, and this base would be a base of 1 over 1.1. And so we can see that the different y values would be bigger or smaller depending on whether the base is bigger or smaller on the left or on the right-hand side. And so I'll just put that exponential decay case picture in the lecture notes. Okay, moving on then. Questions are, what are acceptable bases for exponential functions? We've discussed already that acceptable bases are positive but not 1. So base is greater than 0 and not equal to 1. Or we could write that as saying that the base is contained from 0 to 1, union 1 to infinity. Now state the right and left end behaviors of b to the x using limits. Again, that depends on whether base is between 0 and 1 or from 1 to infinity. So this is the decay case, and these base values are the growth case. So if we are looking at decay, where a base is contained from 0 to 1, we have a graph that looks like this, and we would say the limit as x approaches negative infinity on this b to the x function is positive infinity, and the limit as x approaches positive infinity on the same graph is equal to 0. If we are looking at the growth case, then we are considering base values that are greater than 1, and the picture looks like this. And we would say that the end behaviors are the limit as x approaches negative infinity on this graph of b to the x would equal 0 on the left end, and on the right end, the limit as x approaches positive infinity on the graph of b to the x equals positive infinity. Again, we have horizontal reflections if we have the same b, but or reciprocal bases because we have a negative in the exponent to get horizontal reflection. So let's transform a basic parent function. And if we look here, we notice that the basic base is 2. So the parent function is y equals 2 to the x. And we can plot that graph. 0, 1, 1, 2, 2, 4, 3, 8, and 4, 16. I don't have enough room. And over here we have negative 1, a half, negative 2, 1/4, and a horizontal asymptote over here. Try to make this increasing the whole time, because we notice that from the table of values, as x increases, the output or power values, the y values, increase. So we have a monotonic increasing function for 2 to the x. So let's take our transformed function, put the equation into transformational form, and we notice that the basic function is 2 to the. It's a little bit difficult to see this as an operation, but the exponentiation is this little caret, or to the. So 2 to the x is the operation. So this is the function f. And so 2 to the right here is the basic function, and anything that is happening outside of that is being done to y. So the negative here is a vertical reflection. So when we list our transformations, we have a vertical reflection, we have a horizontal translation of -1, and we have a vertical translation of 3. So the first thing I'm going to do is vertically reflect the graph, and I'm going to do that in green. A vertical reflection takes all of the y-coordinates and changes all of the signs. This is not a partial vertical reflection, it's a total vertical reflection. And so we have the vertical reflection of the parent function in green. Now we are going to horizontally translate left 1 space and vertically translate up 3 spaces. So I'm going to do these at the same time. So I'm going to take a few points like 0, 1, and I'm going to go 1 to the left and 3 up. I'm going to take this point, 1, -2, go 1 to the left and 3 up. I'm going to take this point, 1 to the left and 1, 2, 3 up. 1 to the left, very difficult to see in this graph, and then 1, 2, 3 up. I also noticed that I had a horizontal asymptote, at least on the left end, because I have different left and right end behaviors, but my horizontal asymptote has an equation of y equal to 0. And that horizontal asymptote it's a y coordinate, a y value, so it is affected by y things. It will not be affected by horizontally translating the line 1 to the left, but it will be affected by moving it up 3 spaces. So my new horizontal asymptote will be located at y equal to 3. And then that will really help to guide the rest of the graph after transformation, because I know that my graph still will not, from green, cross the red horizontal asymptote. And so we get something that looks like this. Okay, so the domain of the red function. The domain is a set of exponents, and there are no restrictions on exponents, so x is contained in the reals. The range is bounded. We know that the original parent functions are not crossing or touching the horizontal asymptotes, so the transformed function also does not cross or touch the horizontal asymptote. And we know that y is going to be less than 3, but not equal to. Okay, moving on, if we have some exponential models, one thing we would like to be able to do is apply these graphs and shapes to solving problems. So whenever one quantity, say y, grows or decays exponentially as another changes, and the other would be the input value of x, we say that the relationship between the two quantities x and y is exponential. And the basic model or equation that we will use to relate these quantities is y equals a times b to the x. From a transformations point of view then, we could see that we have a vertical reflection or scale of a on the parent function of b to the x. Again, if b is between 0 and 1, we have decay, and if the base is greater than 1, we have growth. So what we want to do is to determine the equation of the exponential function whose graph passes through these 2 points. Well, in order to come up with the equation for any function, whether it is linear, quadratic, rational, whatever, we have to solve for the non-x and y letters. The non-x and y letters are called parameters. And in the exponential model, we have 2 parameters, a and b. So when we want to solve for a and b, since we have 2 unknowns, we need to come up with 2 equations. And therefore, we are required to come up with 2 points that will give us 2 equations to solve for a and b. So the first thing we are going to do is substitute in the first point, -1 for x and 6 for y, giving us 6 equals a times b to the -1. The second equation, taking the second point and substituting 3/4 for y and 2 for x, we end up getting 2 equations for x and y. In the past, we have added or subtracted or substituted for the unknowns, but in this case, the a and the b are joined by multiplication. And so what we are going to do is recognize that a is identical. It's a to the exponent 1 in both cases. So I'm going to take one equation and divide it by the other. I'm going to take equation 2 and divide it by equation 1. And if I do that, the left side of equation 2 is 3/4, and it's divided by the left side of equation 1, which is 6. Meanwhile, the right side of equation 2 is a times b squared, divided by the right side of equation 1, which is a times b to the -1. What this allows me to do is eliminate the variable a. So I have one equation with one variable left. And now 3/4 divided by 6 is the same as 3/4 times the reciprocal of 6, which equals b squared divided by b to the -1. We keep the base and subtract exponents. So now we have 3 and 6 reduce, and we have 1/8 is equal to b to the exponent 3, and we should be able to recognize that 1/8 is 1/2 all cubed, and in this case, if the exponents are the same, the bases must be equal. So we get that b is equal to 1/2. Now we substitute this b value back into equation 1 or 2, and we can solve for a. I think I will substitute it into equation 1. And so taking this and substituting into equation 1, I get 6 equals a times 1/2 to the exponent of -1. 1/2 to the -1 is the same as 2. And from here we get that a is equal to 3. So to determine the equation of the model, we need to restate the final answer, which is the model y equals a times b to the x with a and b substituted in. So our model is y equals 3 times 1/2 to the x. This is not the only way to solve for a and b, but it's one approach. Let's just take a look at the graph of 3 times 1/2 to the x and confirm that it passes through the 2 points that we were given. We were given the points -1, 6, and there's the point on the graph, and we were also given another point 2, 3, 2, 3/4, and that point is also on the graph. So we can see clearly that we have indeed come up with an exponential function of the form y equals a times b to the x that satisfies the criteria, passing through the points that we are given. Later on, we are going to talk about financial investments, compound interest, simple interest, etc. as an example of exponential growth, and we'll see that example in an assignment. So there is our graph with the 2 points that we were given. So this is the graph of y equals 3 times 1/2 to the x, or we could write it as 3 times 2 to the negative x, passing through the given points -1, 6 and 2, 3/4. And it's hard to see the asymptote here. There it is. All right, moving on, let's take a look at the inverse partner to exponential functions, which are logarithmic functions. First of all, we want to look at the expression log base 2 of 8. The expression log base 2 of 8 means, and I'll write it out, it's a question. What is the exponent on the base of something to get the power of something? Well, the base is 2. The base of the logarithm is the subscript or lower number, and the power is what you're taking the logarithm of. So because we have memorized our powers, squares, and cubes, we know what exponent we put on 2 to get 8. Because 2 cubed is 8, therefore log base 2 of 8 is equal to 3. These two statements are equivalent. The only difference is we have the same base, and we have the same power, and we have the same exponent. From here we have base is equal to 2, exponent is equal to 3, and the power is equal to 8. The only difference in how these two expressions or these two equations are written is who gets isolated. In the exponential case, the power 8 is isolated. In the logarithmic case, the exponent 3 is isolated. In part B, it asks, in the equation y equals 2 to the x, what does each value represent? Okay, 2 represents the base, x represents the exponent, not the power, and the output of a base raised to an exponent, namely y in this case, is called the power. In the inverse function, if we have an inverse function, then x and y swap, and so x would represent the power, and y would represent the exponent. So if we want to come up with the inverse equation for y equals 2 to the x, we say that x and y swap places, so we get x equals 2 to the y. And just looking graphically, as soon as we swap the variables x and y from the original parent function, then x is equal to 2 to the y should be a reflection through the line y equals x. And in fact it is. So this is the inverse function. The problem is we generally like to isolate y. And in order to isolate y, we would have to use a new operation or expression that may be brand new to some of us. So y equals log base 2 of x is the same as saying x equals 2 to the exponent of y. We can see that the purple and the green graphs are the same. Let's keep that in purple, and we'll add that to the lecture notes. Remember that inverse functions are reflections through the line y equals x. Okay, so if we want to isolate for y, we see that we have to undo 2 to the x. So the undoing operation of 2 to the thing that we must apply to undo 2 to the is log base 2. So we're going to read this as log base 2 is the inverse or undoing of 2 to the. And so if we apply log base 2 to both sides, we get log base 2 of x is equal to log base 2 of 2 to the y. And the log base 2 and the 2 that cancel, leaving us with y on the other side. So we get y equals log base 2 of x is the inverse function for the exponential function 2 to the x. All right, let's complete the table of values. If x is equal to 1, 2, 4, 8, 16, we have to remind ourselves what this means. Y equals log base 2 of x is equivalent to saying 2 to the y is equal to x. So in this case, the base is equal to 2, the exponent is equal to y, and the power is equal to x. The power is whatever you're taking the logarithm of. And when we see log base 2 of x, you're going to read it as, what is the exponent on base 2 to get the power x? The exponent is y. Okay, so remember that we used to have y equals 2 to the x, where x was the exponent and y was the power, but we've swapped x and y to get the inverse. So this was in the original case, and it's at this point I want to state, this is why we do not say 2 to the power 3, because the output is called the power. And if both of these are called the power, and then we swap them, we've completely lost track of who is what quantity. So right now, x is powers, and the output values are exponents. So let's just think of it this way. As far as base 2 is concerned, if the power is 16, what is the exponent? Well, the exponent is 4. And if the power is 1024, what is the exponent? The exponent is 10. And if the power is 2, what is the exponent? 1. So you can fill in the rest of the table. The power of 1 has an exponent on base 2 of 0. 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 5, 6, 7, 8, 9. We know that it's not possible to get a power of 2, because when we were looking at the table of values, when we had x and 2 to the x, we had things like, the powers were things like 1, 2, 4, 8, 1/2, 1/4, 1/8, etc. And every time we went up in the table, we were dividing by 2. Continuing to divide by 2 will never get to 0. So there is no exponent that produces a power of 0. And in this case, we'd say that that exponent is undefined. Similarly, if we keep dividing a positive number by a positive 2, we will never get a negative quantity. So it's impossible to get negative powers. There is no exponent that produces a negative power. In this case, we get exponents that are non-real. We won't explore this too much, but we will take a look at what the graphing calculator has to say about that. If I try to work out the logarithm of 10, it will give me an answer. Log base 10 of 10 says what is the exponent on 10 to get 10? Well, the base 10 raised to the exponent of 1 gives the power of 1. Just as another example, what is the log of 100? This is an automatic base 10 here on logarithm, and we get base 10 to the exponent 2 is 100. And so what if I were to take the logarithm of negative 10? In this case, we get a non-real result. So we have something like the square root of negative 1, but not using square root functions, this time using logarithmic functions. So we do want to be very careful when we are looking at the kinds of powers that we get. A power of 0 comes from an undefined exponent, and a negative power comes from a non-real or complex exponent. Okay, continuing on, we have the graph of 2 to the x and y equals x. So again, we should be able to easily come up with the inverse function. I'll just write that this is y equals 2 to the x in blue. If we have a horizontal asymptote at y equal to 0, then in the inverse case we have a vertical asymptote at x equal to 0, because y turns into x. And this is on the negative side of the x-axis, so the vertical asymptote will be on the negative side of the y-axis. We had a y-intercept at 0, 1 on the original function, so we have an x-intercept at 1, 0 on the inverse function. And the rest of the points we just plot 2, 1, 4, 2, 8, 3, and the graph grows very, very slowly. And we notice that we have no graph on the left side of x equal to 0 because this is where we have non-real results for the exponents. The two functions are graphically related because they are reflections through y equals x. Okay, let's state the domain of y equals 2 to the x. The domain is the set of x values and x represents the exponents. There are no restrictions on exponents, therefore the domain is x contained in the reals. The range of y equals 2 to the x is focusing on the y values, and y represents powers, and all of the power values can't be negative or 0, so the powers must be positive. I should have put that in blue. Let me see if I can just change the color here like this. Just change the color with properties. There. And this one I'll just write in blue again. Okay, so that's for our blue function, the y equals 2 to the x. For the red function, the domain refers to x, but x is now has been swapped from y, so x now represents the power. And so the power still cannot be negative or 0, so powers must be positive. Or we take the domain of the range of the original and make it the domain of the inverse. Similarly, the range of y equals log base 2 of x refers to the set of exponent values, and there are no restriction on exponents, so y is contained in the reals. But that makes sense because the domain and the range, the domain of the original becomes the range of the inverse. Okay. Let's take a look then at our new domain restriction number 3. But before we do, let's just review. Our domain restrictions so far number 1 said denominators cannot be 0. If so, we end up things like y is undefined, which produces a vertical asymptote of the graph, or y is indeterminate, which so far produced holes or jumps in the graph. The second domain restriction was that radicands of even roots had to be positive or 0. And if we had something like y equals x squared plus x plus 1, we could get a quadratic discriminant of b squared minus 4ac, which was 1 minus 4, which is negative 3. And that tells us that there are no x-intercepts because we would have a non-real result. So graphically, this might turn into something where we have a parabola with a y-intercept at 0, 1, but no x-intercepts, concave out parabola. Our third and newest of 4 domain restrictions is that powers must be positive. We know powers cannot be 0 or negative because going through the table of values, as we saw a moment ago, we're continuing to multiply or divide by 2, and we never end up taking something, dividing it by 2 and getting 0. We never take a positive and divide by 2 and get a negative. So powers can only be positive. And we see that if we look at the basic y equals 2 to the x graph, y is the set of powers, and y does not lie on or below the x-axis. So powers must be positive. Powers, which is the set of y values. Okay, so powers must be positive, then we could take a look at this expression or this function and determine the domain. So we have the function y equals log base e, where e is approximately 2.718, is equal to, log base e of x squared minus x minus 6. So let's just recall, when we have y equals log base e of stuff, e is the base, the exponent is the output of the logarithmic function, so y is the exponent, and the stuff we are taking the logarithm of, x squared minus x minus 6, is the power. So we know that powers must be positive, and the power is x squared minus x minus 6 must be positive. So we solve this inequality graphically. We can do it fully graphically or with a sign chart because we don't completely need the graph. What I'm going to do is factor this, and we get x plus 2 times x minus 3. From here I'm going to do a sign chart, and on my sign chart for x I plot -2, I plot 3, and I know that if x is equal to -2, then the power equals 0. When the power is equal to 0, my logarithmic graph will have a vertical asymptote. So x equal to -2 is not part of the domain. In other words, I do not want the power to equal 0, I only want it to be positive. Similarly, I don't want x to be positive 3 because then the power would be equal to 0, which does not satisfy the domain restriction number 3. So we put our factors here, x plus 2, x minus 3, we fill in the sign chart, and we know that x squared minus x minus 6 is positive, then negative, then positive. We want powers to be positive, so we want x to be less than -2 or greater than positive 3. So therefore the domain, let me put it in blue, domain, remember, is the set of x values that produce defined and real y values. So the domain is x less than -2 or x greater than 3. Let's confirm this with the graph of the function so that we can be sure that the domain is what we algebraically and numerically solved for. So we're looking at the graph of y equals the natural logarithm, which is the logarithm with the base of e, 2.718 approximately, where e is the natural number. So we use L for logarithm, N for natural, when it's log base e. And the power is x squared minus x minus 6. If we look at this graph, we do indeed see that x equal to -2 and x equal to 3 produce vertical asymptotes, and the graph is produced to the left of x equals -2 or to the right of x equals 3. Any x values in between would produce non-real y values. Okay, so we can confirm our graph to have the same domain as what we found using the sign chart. And the last couple of questions here. What features do all logarithmic graphs have? Well, if you recall, I asked what features do all exponential graphs have? They all had the same y-intercept at 0, 1 and a horizontal asymptote at y equal to 0. And by all, we mean the parent. Let's talk about the parent log functions. The parent logarithmic functions are of the form y equals log base b of x, where b is the acceptable base from 0 to 1, union 1 to infinity. So bases that were from 0 to 1 were the exponential decay functions. So log bases from 0 to 1 are the inverses of exponential decay. Meanwhile, bases for the exponential functions that were greater than 1 produced exponential growth. So these functions log base b, when b is greater than 1, are the inverses, or the reflections through y equals x of the exponential growth functions. So the features that all logarithmic graphs have will be an x-intercept, if they have this form, located at 1, 0, and a vertical asymptote at x equal to 0. And that was on the, well, I'll just leave that, x equal to 0. Okay, state all the transformations performed on the parent function to produce this graph. So again, recognizing the parent function is the first step. We have y equals log base 2 of x, which is the inverse of y equals 2 to the x. So maybe it's easier for you to sketch y equals 2 to the x. I'm just going to do that in green very quickly. We should have no problem plotting some points here because we've memorized our tables of values. And in green is my exponential growth function, y equals 2 to the x. If I take that green graph and reflect it through the line y equals x, I would get the basic logarithmic function with a vertical asymptote at x equal to 0, an x-intercept at 1, 0, a point at 2, 1, 4, 2, 8, 3, 16, 4, etc. 1/2, -1, 1/4, -2. And so I will get my basic logarithmic graph with a base of 2, which is the reflection through the line y equals x of the exponential growth function y equals 2 to the x. So if I'm not very good at graphing the log function, I can start off graphing the exponential function, get the inverse graph, and then perform transformations on the blue graph. So now putting this equation into transformational form, I get y minus 1 equals negative log base 2 of x minus 2, and anything that's being done after the logarithm is a y transformation. So this is negative times y minus 1 equals log base 2 of x minus 2. So I have a vertical reflection, I have a horizontal translation of positive 2, which means 2 to the right, and a vertical translation of positive 1, which means up 1. So I'm going to do the vertical reflection in purple, and vertically reflecting means I take every y coordinate and change the sign. So this part of the graph that lies below the x-axis will lie now above the x-axis. And these y coordinates are things like 1, 2, 3, 4. They're going to go down to -1, -2, -3, and -4 for the same x values. Okay, so the purple graph is the vertical reflection of the blue logarithmic graph, and then performing the horizontal translation of 2 to the right and the vertical translation of 1 up. I go from this starting point, my x-intercept transforms over 2, up 1. This point over 2, up 1. This point over 2, up 1. This point over 2, it's hard to see the lines here, over 2, up 1. Over 2, up 1. And I also have my blue vertical asymptote is going to be affected by the horizontal change because x is the horizontal variable. So I have a new vertical asymptote at x equals to 2. I have a red point there, that's a bit misleading. And I have, let's take one more point over here, something like this point is going to go over 2, up 1, something like that. So my graph is going to come like this and stay to the right of my vertical asymptote. I don't want it to get too close too soon. So the red graph is the final function. So if we label all the relevant features, we have an x-intercept, we have a vertical asymptote. The x-intercept we saw, if we took this purple point, I will highlight it. This purple point went over 2, up 1, and so this purple point we had seen was 2, -1, we go over 2, up 1 to 3, 0. So we have the x-intercept at 3, 0. We have a vertical asymptote at x equal to 2, an x-intercept at 3, 0. We didn't end up crossing the y-axis still, so we don't have a y-intercept. We have a domain, the set of x values that are acceptable. Well, powers must be positive, so x minus 2 must be greater than 0, says that the domain is x is greater than 2. And the range is the set of exponent values. There is no restriction on exponents, so the range is all reals. Well, that concludes our 2-section video on 3.1 and 3.2. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.